Hi everyone, welcome to this M2D2 talk. Our speaker today is Gary Tom. In this presentation, he will be talking about how to calibrate and generalize probabilistic models on low data, on low data chemical data set. Gary is a chemistry PhD at the University of Toronto, working with Professor Alan Asperger. Prior to that, he completed his master in condensed matter physics at the University of British Columbia and has a bachelor in physics and life science at University of McGill. His research focused in probabilistic prediction and Bayesian optimization of molecular properties for process optimization and molecular design. He is also very interested in generative modeling for inverse design and inverse design of chemicals using reinforcement learning, variational autoencoders, and genetic algorithms. Thank you so much, Gary, for accepting to present your work to us today, and looking forward to it.
Yeah, thank you for having me, the organizers, for inviting me to come and talk about what I've been up to. And thank you for everyone for attending and listening to what I have to say. So like it was said in the beginning, I'll be talking about this project, DIONYSUS, on the calibration generalizability of probabilistic models on low data chemical data sets. If you have any questions along the way, feel free to just interrupt me. You can do the raise a hand function, or you can just type in the chat. I can see them. There's some chat messages. So feel free to interrupt me at any time. And there's also time at the end for questions. So to sort of motivate why we're interested in looking at uncertainties when we're doing chemical sort of analyses, if you had to pick a drug, for example, let's say the left and the right here, I have the IC50, so that's the concentration for effectiveness of a certain drug. So the lower the concentration, the more effective the drug would be. Let's say you had to pick a drug, and these are predictions given to you by your model. You would probably pick the one on the left, right? So this would be the lower value. But if we consider the fact that maybe our model was trained on some data that was very biased, or it's not actually quite certain, so we're looking at the uncertainty of the model or the confidence of the model, now it's a little more difficult to try and see which one you would pick, right? So here I've added some uncertainties. These are all hypothetical. It's not truly a prediction. But now that we're looking at the sort of error bars on these predictions, you have to sort of understand which one, it changes your decision, right? So personally, I would probably still pick the one on the left, just because the error bars are pretty small and the values are lower, even though technically the prediction on the right molecule can go to a lower concentration, so a higher effectiveness. But if we were also to say that the models actually have a tendency, different sort of calibrations, so the estimation of the uncertainties can be overconfident or underconfident, now the question becomes a lot more nuanced, right? So now the one on the left, even though the uncertainty is quite small, we also know that this model tends to produce uncertainty estimates that are too confident, in which case maybe 0.5 is not the right number. And on the other hand, looking at the molecule, the prediction on the right, we can see that maybe it's underconfident, in which case the error bar here is actually too large. So this is the motivating idea here of why we're interested in looking at uncertainties of probabilistic models. So with that in mind, we know that uncertainties are important in decision making, and oftentimes we use it for things like Bayesian optimization for experiment planning or discovery of molecules in an automated lab setting in chemistry. We need to think about the model calibration. So looking at a probabilistic model, we want the uncertainties to be appropriately estimated, and it should relate to the accuracy of the models, or it should correlate with the accuracy of the models. And also, something else that we want to be aware of is that oftentimes when we're looking at experimental chemistry or biological data sets, we're often looking at much lower data regimes than what computer scientists are typically used to. So instead of looking at tens of thousands, we might be looking at thousands or 2,000, maybe even less than that. just because of how time consuming it is to actually synthesize, characterize, or run assays on our molecules. So we want to ask the question, how well do the probabilistic models that we look at in this project perform on chemical tasks when we're looking at the low data regime? So here we define it as things less than 2,000 molecules, but we also look at smaller data sets. And we also want to know how well calibrated are these uncertainties. So we, in the project, look at 3 different experiments. We have regression and binary classification tasks. And for the first one, it's quite straightforward and it's been done before, where we actually just run the models on our data sets with certain splits. So we study the calibration and the performance of the probabilistic models. In our second experiment, we apply these models in a simulated practical application where we have Bayesian optimization. So we're searching for the best molecules within our data set, given a small subset as a starting point. And then finally, we study the generalization of our models. So if we had some model predicted on some training data, how well can it generalize to clusters further out in chemical space? Chemicals that are not as similar to our training set as we might want it to be. So we do this using something called cluster splits, where we look at the structure and form the splits based on that. It's similar to scaffold splitting, if you're aware of that, but it's a more generalized form of that. And all of these tools are packaged as DIONYSUS on GitHub, and so check it out if you're interested. The data sets that we study, we have more data sets. These are just a subset of the data sets that we're looking at. We look at 3 regression tasks and 3 binary classification tasks. So we have, for regression, we have the biodegradability half-life, which has 150 molecules. We look at the free-solve data set, which has 637, and the Delaunay data set, which is also known as the ESOL data set, which has about 1,000 molecules. And that looks at the solubility of our molecules. And we also do binary classification. So we have the BACE data set, which looks at whether or not a molecule will bind to the human BACE1 protein. We have the biodegradability classification, so whether or not it's readily biodegradable, and also the BBBP data set. So this is whether or not it can penetrate the blood-brain barrier in our brains. And you can see that we try to pick data sets that have a varying number of molecules ranging from 150 up to 1,870. So for our first experiment, quite straightforward, we take our data set, which we then featureize. So we used 4 different featureizations, which we can group into 2 groups. So we have vector features, which are simply just features of just vectors. And we also have graph features where the vectors are allowed to pass messages between the edges. And then we put that into some probabilistic prediction or classification model. So, and we'll go through those. What makes them probabilistic is that they can output an uncertainty. So they typically predict some sort of a distribution. And then that distribution gives us the mean and some variance, which corresponds to our uncertainty of the prediction. And this, again, has been done before. I would like to reference the work from Connor Coley's group and Sunghyuk Ryu's group, which have also studied similar things for different data sets. So the first part, we take our data set and we featureize them. So we do 4 different features. We start with the top panel, panel A. Here we look at a very common feature that's used all the time and sort of the first thing that people do, which is the circular fingerprints. So the circular fingerprints here, or the Morgan fingerprints, we basically go through our entire graph, which is represented by our smiles. And in that graph, we walk through each of the heavy atoms and look at increasing radii of neighboring structures. Those structures are then hashed into a bit vector. So we have ones and zeros, and this represents each of the individual fragments that we observe, or the functional groups that we observe. We also have the Mordred descriptors. Mordred descriptors are essentially a set of descriptors that can all be obtained directly from the graph, and they can range from anything as simple as molecular weight, Boolean values such as whether or not it's an acid, integer values such as how many atoms it has, up to something more complicated, looking at the adjacency matrix of our graph and calculating the norm or the eigenvalues. And then in total, the Mordred feature has almost 1,400 to 1,600, depending on the data set, features. So that number of columns. And those we can input into our models to make predictions. In panel C, we have the graph features. The graph features are essentially taking the graph, the molecular graph that we have, and then encoding it into a set of vertices and edges. So the vertices themselves represent the atoms, and the edges represent the covalent bonds between them. And each of those nodes and edges have their own features. So for example, the vertices can tell us about the atom's atomic number, or perhaps the partial charges on the hybridization of that molecule, or of that atom. And the edges can tell us edge information. So single bond, double bond, whether it's aromatic, so on and so forth. We also have one additional node, which is the universal node. You can think of this conventionally, it's a pooling layer essentially. We have one node that's connected to all of our nodes so that it can extract universal properties. So these are properties of the whole entire graph. So this is the graph representation that we use. Finally, we have our GraphNet embeddings. So what happens is we take our feature, our graph feature, C, and we input it into our GraphNet neural network. GraphNets is sort of an older graph neural network, but it's been shown to be quite effective for making these embeddings. And essentially, we have this graph entering, and we have 3 layers of this graph embedder. And then at the very final layer, we add a predicting layer, which then predicts the properties based on whatever data set we're looking at. So we take the universal node of the final output of our graph embedding and then put it through the predictor and then train it on our properties of our data set. And then we take one step back and then take those universal nodes, the embeddings in that latent space, and then use that as a vector property. So we put that into our data sets. So these are the features that we use. In terms of the models that we use, we have a wide variety of them. We have deep models and we have sort of not deep models. We use NGBoost, which is similar to, it's a gradient boosting method with random forest. So we have an ensemble decision trees. Instead of just outputting directly the prediction, it outputs parameters for distribution. So for our regression tasks, we have it output a Gaussian distribution. And for our classification task, we have it output a Bernoulli distribution. For the Gaussian process, this is essentially a distribution over functions, which we can define based on 2 functions. So we have our mean function. This we use just a 0 because we have no prior knowledge of the mean. And we also have a covariance matrix, which is determined by our kernel function. So this determines the shape of the functions that we are going to observe. We use a very common and standard radial basis function for the kernel. But for the fingerprints, we use the Tanimoto kernel. So this is just a Jaccard distance between our bit vectors. So for the fingerprints, because we're looking at bit vectors, the kernel function here to measure distance is going to be the Jaccard distance. And we fit this to a negative log likelihood, which then gives us our prediction on our outputs. For the deep models that we look at, we have, probabilistically, we have our spectral normalized GP. So this is an example of a deep kernel GP, where essentially the kernel is approximated using a neural network. And here it's a multi-layer perceptron connected to a GP layer, and we have spectral normalization of the weights, which has been shown to improve the distance awareness of the Gaussian process. But this is just an example of deep kernel GP. We also have the GNN GP, where instead of using a multi-layer perceptron, we use a graph neural network. So it's the same graph neural network that we had for our embedder. It's the GraphNets embedder, except now at the end, we train it with a Gaussian process. So end to end, we have our kernel approximated by this GraphNet neural network. And then finally, we also look at Bayesian neural networks. And this is represented in this diagram here, where instead of having deterministic weights, we are going to have distributions of weights. And these distributions are also Gaussian. So this is a stochastic network. What we do is we train it, and then we sample many times. It will give us a distribution of predictions, which from there we extract our uncertainty and the mean of our predictions. So these are the 5 models that we look at. In terms of the metrics of determining what is a good model and not a good model, for our regression predictions, we evaluate the goodness of our model using the R-squared metric. So this is just R-squared between the ground truth and the predictions. Values of 1 means perfect predictions, and values of 0 means that our predictions are only as good as the mean of our data set. So not very good. And we also look at the calibration. At the calibration, there's many different ways that we can look at it. We can look at the negative log likelihood. We can consider different scoring methods. So there's, off the top of my head, I can't remember the other ones, but the one that we decided to use is to consider the reliability diagram. So here, what we have is the C of Q score. Q here is the quantile. So we look at essentially the Z score and see whether or not it falls in the inverse Gaussian of that quantile. So we expect to see C of Q to be equal to Q for a perfectly calibrated model. So this is this dashed line here, if we were to plot out all the values of Q. In the case where we have an overconfident model, this curve will dip under this perfect calibration curve or the line, and then an underconfident model will go over this. So to measure how uncalibrated something is, we look at the absolute magnitude of the area between the C of Q equal to Q and the curve itself. And so this gives us a single score, which we can easily summarize this plot. But this score does not tell us whether or not it's over or underconfident because we're looking at just the magnitude of the area. So this is how we define calibration. Here are some results for our regressors. So for our regressors, for our 3 data sets, we have BioHL, which is the half-life biodegradability. We have the FreeSolve, which is the free energy of solvation, and the Delaunay solubility data set. Here we have the various features demarked by the color of the points and the models by the shape of the points. The error bars here are obtained by bootstrapping from our results. What we observe here is that when provided with enough data, the Bayesian neural network and the Gaussian, the GNN GPs perform competitively with the other methods. So this is for FreeSolve and for Delaunay. We can see that our Bayesian neural network performs very high with the R-squared. But what we do see, and the GNN GP, which is this diamond point here in the lower left, sorry, the lower right. This corresponds to the y-axis here is the miscalibration, so the lower the better, and the R-squared, the higher the better. And what we also see is that the SNGP, so the deep kernel MLP GP, are consistently poorly calibrated, despite predicting very well on the R-squared. So it is not very well calibrated at all and tends to overfit on our data. What we also see is that NGBoost and GP consistently perform quite well on all of our data sets, even the BioHL. So here we're looking at very low amounts of data, only 150 points. So our crosses and our X's correspond to the NGBoost and the GPs. So they perform quite well. in all of our scenarios. What we also see in general is that the Morgan fingerprints don't perform very well for these data sets, but if you were to use the Morgan fingerprints, the Tanimoto kernel GP performs better. So these are the blue points here. So we see that the GPs typically have lower miscalibration and higher accuracy in their prediction. Finally, for all three data sets, we also see that the Mordred descriptors perform very well for all of our data sets. These are the orange points, so consistently in the lower right of our plots, and also that the graph embeddings can actually perform quite well, even in the case of low data. So that refers to these points here. So here we're able, for very low data regime, 150 points, even though the GNN-GP, so the GNN-GP is trained end-to-end with a GP, that actually performs so poorly it's not on this plot at all. But the embeddings themselves, when paired with either the random forest technique or the Gaussian process method, can actually get pretty good predictions and pretty low miscalibration errors. So that's quite interesting. We also look at binary classification. Here we evaluate the goodness of our predictions using the, yep. So there was a question.
Yes, can you go back to the previous slide, please?
Yeah.
In most of this point, most of the figure, we don't see the Bayesian network. We see it like maybe 2 times, but like I was wondering if we were just always out of the chart or what's happening.
So the Bayesian neural network and the GNN-GPs and the SNGP do not show up at all in the BioHL because there's only 150 points here. So the deep learning methods don't work very well for this furthest left plot, but they do show up on all the other plots. So we see Bayesian neural network here and here. We see Bayesian neural network here and here, and also here for the fingerprints. So we do see them, but they don't perform as well as NGBoost or just GPs.
Okay, and is it fair to also conclude from this plot that the uncertainty of the calibration depend a lot on the representation that you use?
Yes, yeah, that's very fair. Yes, yeah. So that's exactly what we're exploring here. What features and what models. And also, I want to caution against making any, you have to look at the trends across the data sets because each data set is very different. We're looking at very different molecules and we're looking at very different tasks. So something might perform well for one model and something might not perform so well for another data set, but you can't conclude that it's the same across the data sets just because the tasks themselves are quite different.
Okay, perfect. Thank you.
Yeah. So we also do something similar for the binary classification. So here we look at the OROC score. The OROC score of 0.5 corresponds to just randomly assigned predictions. So anything greater than 0.5 means you have something of a classifier. The perfect score is 1. A reliability diagram here is actually quite straightforward compared to what we saw in regression. All that we do here is we bin the results and we would expect whatever confidence, so this would be the probability of observing in our Bernoulli distribution, a yes or a no. We would expect that confidence to be equal to the accuracy of our model. So if I flip a coin, it's 50% chance. I would expect 50% accuracy if I predicted heads. So this is the plot that we would end up getting if we plotted this. And the same idea here to extract a score from this is to just look at the area between the perfect calibration and the binned values. Something I do want to point out here is that because we're looking at so few points, what we observe is that the miscalibration the accuracy can vary quite a bit. This has to do with the fact that in our bins, typically there are very few points in a single bin, just because we're starting with very few points in our data set. So someone asked a question, okay, a question for later, but I could answer it now. Are all 1800 Mordred descriptors used or only a subset? Could one evaluate with the length parameters RBF kernel, which are the most important descriptors? Yes, so we don't look at feature importance in this work, but we also, so that's the second half of the question. But the first half of the question, no, not all 1800 are used. We filter out a portion of them. So we filter out, we filter out the invalids. So not all features will be properly evaluated. And so those are dropped, those columns are dropped. And then we also remove 3D features. So the Mordred package also gives 3D features. So we actually only end up with 1400. Yeah, but we don't look at the feature importance. The thing with Mordred descriptors as well is that there's a lot of redundancy in each of the columns. So I would expect that there will be quite a bit of correlation between some of the columns, but we also do not explore that in this project. Yeah. Okay. So yeah, Evan had a question.
Yeah, sorry. Why don't you show the GraphNet accuracy on here? Or am I just missing one?
Which one?
The red line.
Sorry. So what's wrong with it, or?
Is it there? I was just curious. I was curious how the accuracy of the GraphNet.
Oh yeah, you're right. It is missing. This.
No worries.
Oh yes, this is. It's missing because So this plot was just to show an image of what one of these plots look like. The reason why we don't show GraphNet is because GraphNet corresponds to the graph feature, and the graph feature can only be inputted for the graph neural network. So here we're looking at the Bayesian neural network calibration.
Oh, okay.
So
Yeah,
actually the GraphNet, yeah, it's not used here, but it's still in the legend. So I'll have to fix that. So thanks for catching that. Okay, so here are the results for the binary classifiers. What we do observe, first of all, is that the value, so again, the y-axis here is the calibration error, so the lower the better. And the OROC score on the x-axis is the higher the better. What we observe here is that all of our models actually have pretty high OROC scores for these data sets. So it makes it quite hard to discern which one is better, especially with confidence. But another thing is that, again, we see very large variations in our calibration errors, as we've discussed before, because of the binning. But we can see some general trends here, at least if we look at the far ends of these little clusters. We see well-calibrated uncertainties when we're looking at the NGBoost algorithm, the GPs, and the Bayesian neural network. Again, we see the best performances here are with the Mordred features. So these correspond to the orange points. But the fingerprints actually perform very well here, particularly when we're looking at the BACE and the BBBP data sets. And it's quite likely that this is because the BACE and the BBBP are both biologically, they're looking at, well, one's looking at binding to a protein and one is looking at permeability. And these depend a lot on the functional groups that are observed inside of our molecules. So that's something that's well described by the Morgan fingerprints. Again, we observe that the best Morgan fingerprint results are if we use the GPs using the Tanimoto kernel. So these are the X's here in the blue. And of all of the deep models, we observe that the Bayesian neural networks have the best calibration. So these are the squares, they have the best calibration. Again, the SNGPs do not perform very well here. Okay, so for the next experiment, we look at the Bayesian optimization. I don't know if I have enough time, so I might just go a little bit quicker. But we have the Bayesian optimization experiment. So this is just a simulation of what would be, some sort of an experiment where, let's say, we had a very small portion of our data set. So we have some small subset that are measured, and then we want to pick the next molecules that we want to make a measurement on. We don't actually make any measurements. Here we just have our data set, so we can just look up the values. But if we were to simulate this in a lab, this would be the sort of decisions that we are making. So starting from a small subset of our measured data and a series of unmeasured data, what we do is we take that and we train our surrogate model. So these are the 5 models that we had and each of our features that we had. The predictions on these measured points then give us some sort of a score based on the acquisition function. The acquisition function that we use here is the upper confidence bound, where we just add the mean and the variance of our predictions with some weighted values. The next point that we observe, or the next point that we want to make a measurement, is going to be the point that maximizes this acquisition function. And we simulate a measurement by just adding and appending that data point into our set of known points. So after one iteration, we will get a new point and a new point, and we do this for a certain budget. And then finally, hopefully, we find the best molecule, which is denoted by this star here. And so this would represent a successful Bayesian optimization run. Later, we'll also look at what happens when we vary the parameters in our upper confidence acquisition function. So this is what it looks like for upper confidence acquisition. We have the mean value with some weighted value and the variance, some weight beta. And we explore what happens as we vary how greedy and how variance-based our model is going to be. So that will show up a little bit later. For the Bayesian optimization results, we start with 5% of the data. So we randomly sample for 5% of our data. So that is represented by this vertical dashed line. And then once that is fulfilled, we start doing the Bayesian optimization. So we train our models and we use our upper confidence bound to select the next molecule. In a classification task, what we do, instead of adding the mean and the variance, we just maximize the probability. So this is a fully greedy strategy. And this has to do with the fact that Bernoulli only has one parameter to describe the distribution. And the total budget that we look at is 250 evaluations. For the statistics, we look at 30 randomly seeded runs to give us our 95% confidence bounds on our plots, which is represented by the shaded region here. So I think I have all the plots. Yeah. So for each of our data set, we do the same thing. For the extremely small data set, we actually cap it at 25, just because 5% of 150 is a little too few molecules to start with. For the very small data set, like BioHL, what we see is that random search methods are actually quite effective. So we don't see any discernible differences between just randomly searching and our models. For the other plots, it's a little bit different. So we have blue here, which is the Morgan fingerprints. We have the orange color, which is Mordred. And we also have the graph nets for our graph models. So this is GNN-GP only. And we also have as a baseline just random search, and that's the black line. For the other two data sets, FreeSolve and Delaunay, what we observe is the best performance when we're using the Mordred descriptors with the NG-boost, so that's this plot here, and the GPs. And they perform better than the Morgan fingerprints consistently for all of our models and for both of our data sets. And what we do see is that the GP with the Morgan fingerprints, so again, we're using the Tanimoto kernel here, performs better than the NG boost. So if you're using the Morgan fingerprints, using the GP with Tanimoto kernel is quite effective. So we see this also in the Delaunay, where we see faster optimization with the GPs. We see that all of our deep models, with maybe the exception of the Bayesian neural network, do not have enough data to actually train. So the Bayesian neural network with the Mordred features does end up getting the lowest value here in our FreeSolve, but for these models, the SNGP and the GNN-GP, we simply do not have enough data to train. Yes, there's a question.
Yeah. How do you explain the fact that GP doesn't have a good uncertainty, yet when we use it in active learning setting, is kind of allowing the speed up of the experiment?
So GPs aren't necessarily not as good uh, as NGBoost in terms of uncertainty calibration. It's good for some. NGBoost might be better, but actually later on we'll look at what happens when we vary the importance of the uncertainty. So I'll answer that a little bit later. That's okay.
Thank you.
Yes, so that's all I had to say. For binary classification, we also do the same thing. Here we actually start with 10% of the data, just because we have a larger data set. So here we're starting with about 100 molecules. And essentially what we do here is greedy strategy. So we're looking at the fraction of positive hits in our data set. In all these cases, what we observe is that NGBoost and GPs perform the best in all the cases. So again, in the low data regime, we see that the deep models fail. But what is kind of peculiar is that if you look at these deep models at around 300 molecules, so by the time we have accumulated 300 molecules, we start to see an uptick in performance for these data sets. For BNN, same for SNGP and GPs. We see this for all of our data sets. So that's quite interesting. We see that the Morgan fingerprints, which we observed before, to perform slightly better than the Mordred descriptors. And this is sort of expected because, again, we saw the BACE and the BBBP perform quite well with the Morgan fingerprints. So that's what we see. And to summarize everything, we have essentially this table here where we look at the number of hits achieved by the Bayesian optimization. And the errors here is the 95% confidence interval. For a regression, we define a hit as a molecule within the top 10% of the data set. So that's how we add that up and we plot that and we put this in this table. And so what we observe is typically the Mordred features are quite good for our regression tasks at least. And we also see that the Mordred features and the Morgan fingerprints perform quite well for our classification tasks. In most of our tasks, the GPs actually have the best optimization, which leads us to sort of exploring the effects of our acquisition function and exploring the effects really of how important is it to get the calibration right and how important is it to get the accuracy right. So here are our various plots. So let me explain what we're looking at. Here we'll only look at Mordred features for the Delaunay dataset. We look at it for only the two models that performed well for these experiments. So we have the GPs and the NGBoost. And we vary the parameter here, beta. And as beta increases, the more variance-based our acquisition function will be. So the more important the variance will be. And so we have the optimization traces here. And on the panel B, what we have is we have a test set that's extracted from our data set first. And as the optimization proceeds, we evaluate the R squared and the miscalibration error on the test set as we do the Bayesian optimization. So this goes back to the question that was asked earlier. Essentially, why is it that NGBoost performs better, but it optimizes better? So what we actually see here is in this plot, for low beta, this means less variance based, so more greedy strategies. We actually obtain higher miscalibration. So these are these lines here, and lower R squared. And this has to do with the fact that because we're looking at starting with a small data set, and we're only for the next points that we end up adding to our data set are values that are already known. So essentially, we're only willing to stay within the training set and not exploring out of it. We actually get lower performances. With higher variance, we have a more diverse set because now we're looking at higher variance values, so predictions that are less confident, and then making those evaluations. So the training set ends up becoming more diverse as we look at larger variance acquisition values. And so that's why we see higher R squared and lower miscalibration in both cases when we're looking at very high amounts of beta or high levels or high value of beta. In our optimization traces, what we do see is that typically the value of about 0.25 for beta gives us the best optimization. It's not very clear for the NG boost, but for the GPs, we can see there's some difference here between 0.25 and 0. So those are probably the best values for, in this case, an active learning scenario. Finally, we look at the generalization and ablation study. So here we want to predict out of distribution molecules from different different clusters within our data set. So we're going to create these clusters, and then we're going to allow the model to slowly see more and more of this training data and observe how the performance changes as we change the training size, of the sets. The clusters can be generated with any data set. So if you had your own data set, you can create these cluster splits yourselves using our code. And the structures themselves are generated using the Morgan fingerprints, which encodes the structural information. This is appended with the target information, which we then do a dimensional reduction, and then we do a DV scan to cluster the reduced features. These clusters then look a little bit like this, where we can see that similar structures end up clustered together in the same cluster and also observed close together inside of this feature space that we've created. For very large clusters that span a large part of the feature space, we can see that there's some variations within the clusters as well. So this algorithm gives us a set of different clusters. We then take these clusters and generate our training and validation as well as a test set. The test set itself is diverse across all of our clusters, and we have our training and validation, which we essentially permutate between each of the different clusters to create increasing amounts of data as we progress. So these test sets are created by iterative stratification to ensure that the test is diverse across our clusters. The samples of different permutations are then stacked, and we use a training and validation set of 85 to 15%. And finally, we only use the Mordred features here just because we have too many things to look at. So to simplify things, we only look at the Mordred features, which we already saw performed quite well previously. So here are the results for regression. So we perform this on all of the models, and we get the R-squared score and the absolute miscalibration area. On the x-axis here, we have increasing percentage of the training set. So it goes from 0 to 1. And so what we observe is that the deep models, and this is something that we saw in the Bayesian optimization as well, the deep models struggle to perform up until around 300 molecules. So again, we see this 300 molecule point where we see this uptick for the deep models, sudden jump in performance here for GNN-GP, BNN, and SNGP. We see that the GPs are not as robust as the NG boost, especially when we're looking at the very, very low data regime. So this side of the plot, we have higher performance for the NG boost, but it achieves higher performance as we get more and more of the training set. What we also see is for the miscalibration for our GP model, so the SNGP, the GP itself, and the GNN-GP, we sort of have this increase in the miscalibration for some of our data sets, which might have to do with the fact that the GPs end up becoming very underconfident when we start looking at clusters that are outside of the training set, since we're looking at kernel distances for the GPs. We do the same for the classification set. And again, we observe something peculiar. Remember, these data sets are about 1,000 in size, 1,500. So again, what we see is this sudden jump in performance when we're looking at around 300 molecules. So at 300, we can actually get pretty good performance for these deep models. We see that both the NGBoost and the GPs perform similarly, but the GPs are again able to reach higher OROC scores as we get more of the training data. And finally, there's this kind of strange little dip here for the BACE dataset. We hypothesize some reasons as to why we observe this dip in performance for the BACE, and it might have to do with the fact that the BACE clusters might be predominantly in 2 different clusters. So right at about 50%, we start looking at more diverse molecules, which ends up reducing the predictions, the accuracy of our predictions and the calibration. This is just a hypothesis for why we observe this sort of dip in the BACE. So a question for Mark. Even in the high data regime, the GP performs better than the deep learning models, correct? For some of them, yes. So for BNN and GNN, they do not perform as well as the GPs. SNGP does perform quite well. But again, in the high data regime here, high data is about 1,300. So it's still arguably quite low data for you to train something like a Bayesian neural network on it, or a graph neural network. Yeah. Okay. And as a metric of generalizability of the models, what we do here is we look at the median of these curves to kind of give a number as to how generalizable our models are. So the median values here correspond to the R squared, the median R squared. And so for the GPs, consistently we see the highest median values, and also with the NGBoost for the BioHL dataset. Okay, so this wraps up my talk. Thanks for listening. I'm going to go through some of the recommendations and practical insights. If you ever are approached by a chemist, to do some machine learning for me, or like, here's my data, please do some machine learning. In general, the Mordred descriptors are quite robust, regardless of the model choice. So we saw pretty good performance for Bayesian neural networks and Mordred descriptors. If you're using Morgan fingerprints, using the Gaussian processor, the Tanimoto kernel works the best at low data regime, even when we compare it to the NGBoost random forest method. Additionally, the Mordred plus the GPs or the NGBoost is a solid choice if you're not doing any sort of hyperparameter optimization or any model exploration. It's a good starting place. We see that NGBoost is the most performant when we're looking at even less than 100 molecules, so very, very low data regime. And we see that GPs generalize better than NGBoost in general because we're looking at the distances in our feature space. For deep learning models, it suffers at less than 300 molecules, but once we go past 300, there's a sudden upshoot in the performance and the miscalibration drops, but it really becomes competitive when we look at more than 500 molecules, and even then the GPs can often outperform them. But it's possible to train a deep learning model with around 300 data points here for these data sets. We see that the GNN GPs and the Bayesian neural networks are calibrated and perform well when we're looking at more than 500 molecules. The SNGP, not so much. And finally, we see that the the graph embeddings can be quite expressive features, even when we're looking at just 150 molecules, provided that we pair it up with something like GPs or NGBoost. So this is my conclusion slides. Some future work that we can think of doing is maybe multi-label regression and classification, and also optimizing the models for each of these data sets and features. We do not do any hyperparameter optimization for these models here. And yes, so this is my group. I want to thank my supervisor, Alon, as well as my collaborators, Benjamin from Google Brain, and Riley, who's also in my group as a grad student, and the other authors. So thank you.
Perfect. Thank you so much for the talk, Gary. If you have any question, please raise your hand or just write in the chat. I go ahead with the first question. One type of method I was looking for, but I didn't find in your study was ensemble methods, like just pure random forest or assembling of some deep learning method. Because in terms of uncertainty calibration, and there have been proven to be times and time again like the most robust one. So was wondering if you have tried something like that or
Yeah, so we do the NG boost is a random forest technique. Oops.
is a boosting, right? Is boosting and assembling are kind of slightly different, if not quite
Oops,
different.
sorry. Yeah, so random forest also gives us we didn't look at random forest. It would be another model that we can look at. The random forests would give you uncertainties based on consensus. So here we wanted to do a more we call it a Bayesian approach rather than frequentist approach. So instead of just so there's other methods too that you can do for the deep models. We can do dropout Monte Carlo. We can do there's many different models that we can look at. In this case, we decided to focus on probabilistic models where we have some sort of a prior, so either Gaussian or Bernoulli. So we didn't look at random forest.